Okay, this lesson here is on the introduction to the derivative concept, a really important lesson, and we're going to start things off just by talking about a graph. So we're going to take a look at this graph here, and we're going to relate this to some of the earlier content that we talked about. So I'm going to call this T for time, and then S over here can stand for position. And then the basic idea that we talked about is you can have a window of time, right, from A to B, and then we're going to locate these points directly on the graph. Okay, so we have these locations here, and so we can call this A and then S of A, this point here, and then this one is B, S of B. And then if we connect these 2 points, we're going to have a secant line to the graph. So we'll do that so we can see it. So we'll take these 2 points and just connect them with a line. And so this gives you a secant line, and we can talk about calculating the slope of that line. So what we can write here is the slope of this line, right? This is a change in y over a change in x. Okay, so we can subtract our y coordinates and then divide by the difference in the x coordinates. So I'm going to write S of b minus S of a, subtracting the y's, and then downstairs you have b minus a. So remember, if S stands for position, then this tells you how far you traveled. So this is a distance. And then T here stands for time. So you might remember this kind of ratio in algebra, right? Distance divided by time. This is equal to a rate. So the important thing to grab from this is that the rate that we're talking about here is an average rate of change, because we're talking about a rate over a certain interval, right, from A to B. But notice that when we calculate this rate, we're only using the endpoints. We're only using A and B, and also S of A and S of B. So the concept here, if you think about this picture and what it means, right, this is a secant line, but the big thing is this, is that this represents an average rate of change or an average velocity, right, over the interval A to B, because we're talking about rate here. Okay, so what we're going to be talking about in this lesson is letting B approach A. So if we were to drag the second point and let it get closer to A, and then we come up to the graph and identify this new point, notice that we're still going to have a secant line. So I'm going to connect this so you can see it again. So you still have that secant line. But as we continue this process, letting the second point get closer and closer to the first, right, at some point we're going to have these 2 points coincide, right, where the 2 points are so close to one another that they become one. So the idea here is that you're going to have a line that just kisses the graph right at t equals a. So I'm going to highlight that in green. Okay, and this is what your line looks like. And as we saw in an earlier video, this line here is called a tangent line. So the secant lines pass through at 2 distinct locations on the curve. The tangent line just touches the curve at that one point. So the thing that is different here right, we are still talking about a slope here, but this here is the slope of the tangent line. Okay, so the fundamental difference here is we're no longer talking about having 2 discrete points on the curve, so we're really not talking about an average velocity at all. So as we let B tend to A, then we're getting closer and closer to A, and we're shrinking the window, and what this is really giving us is an instantaneous reading when time is equal to A. So the big difference here compared to the other scenario is this is an instantaneous rate of change, or it gives you the reading of an instantaneous velocity, right, when x is equal to a. So it's important to look at these and just to compare them, right? So when you talk about the slope of the secant line, we're talking about the average rate of change or the average velocity over a specified interval. And then when we talk about the slope of the tangent line, this is an instantaneous rate of change or the instantaneous velocity when x equals a. So I used this example of time and then also distance because that's a concrete physical example. And we're going to do this here to talk about the basic idea of a derivative. So I'm going to use this same picture. So you have probably heard some of these terms. This is one way that we classify this, or we give it this name. So we can talk about derivatives or the operation of differentiation. Okay, or you can use this term here. So I'm going to do a very similar development here on this graph. So this way we can talk about the general definition of how to take the derivative of a function. So this is going to look very, very similar. I'm going to identify a couple of points on this graph. Okay, so one of them is x, and then we move to the right. So this is x plus a little bit, x plus h. And I'm going to identify both of the points right on the graph. Perhaps we'll call this graph f, just like this. Okay, so just like our earlier position example, I'm going to label these x and y. So you can see x and f of x, and the same thing here. So you can see x and y. So x plus h, and then we input x plus h into the function f. Okay, so we saw this before, that if you connect these 2 points, you're going to have geometrically a secant line. And so this is going to represent an average rate of change of the function f over the window from x all the way to x plus h. So the main thing we're going to do here now is to shrink the window. So we're going to take the second point and let it tend to the first. So again, what you'll end up with is a sequence of secant lines, and each one will get closer and closer to approximating the slope of the tangent line. So I'm going to put that one right in there. So when h goes to 0, you're going to have a single line here just kissing the graph at this one point. And I'll put that in green again. So this again is the slope of the tangent line. This is the essence of the idea of the calculus derivative. So what I'd like to do is to write down this definition based from this geometric argument. So this is the slope of the tangent line. Okay, so the slope of the tangent line. So what we're going to do is to again look at the change in y over the change in x. But you can see in the diagram, we're letting the second point coincide with the first. So in essence, we're letting h get smaller and smaller. So we can indicate it this way. We're going to let h travel to 0. So we have a limit here. So it's the limit as h goes to 0. And we're going to have the plain old slope, right? The change in y over the change in x. So we're going to subtract these y values here. And then we're going to subtract the x's on the bottom. So x plus h minus x. And that's going to leave us with h. So this is the mathematical definition of how to calculate the slope of the tangent line, aka the derivative. And you can see this definition here. And it uses the idea of the secant line, because if you look carefully, this expression here represents change in y over change in x. So it's this idea of a limit, right, that gives you the slope of the tangent line. So there are many ways that you can notate the derivative. So I just want to go through a couple of those. So this is pretty common here, that this is a mathematical function, right? Y equals f of x. So there's a couple of ways that you can write down or to indicate the slope of the tangent line. The most common one is this notation here with a quote, right? So this is telling you it's not the same as this function, but it's a variation of it. So this is read f prime of x, and it represents the slope of the tangent line. Another way you could write it down is also just y prime, okay? And then sometimes it's also common to see the dy dx notation. So I like the dy dx because it reminds you, right, it's a change in y over change in x, so really the slope of the tangent. So if you take this definition here with this notation, then you can see that this is the definition that you will typically find, or you'll find in math books. It's this one right here. And this is the definition of a derivative. So f prime of x is equal to the limit as h goes to 0 of this expression that we see right here. Okay, so the last thing I want to do is an actual concrete example so you can see what this looks like. So we're going to keep it pretty basic here. So what I'd like to do is we're going to look at this function, right, a pretty familiar one, just a parabola, x squared minus 2, and we're going to find the slope of the tangent line to the graph of this function at 3 different points. Right, so we're going to look at x equals -1, 0, and then also 2. So I'm going to write down the function here. So g of x equals x squared minus 2. And we want the slope of the tangent line at 3 different locations. So at -1, 0, and then also at 2. So the first thing we're going to do is to go back to this definition, right? We're just going to use g in place of f. So we're going to go through and set this up, take the limit as h goes to 0, and then we will have the derivative of g at x, and then we can insert these numbers right in there. Okay, so I'm going to write down this limit definition here. So g prime, this is the limit as h goes to 0. So g of x plus h minus g of x, and then this is divided by h. So you can see we have to use the g of x here, then also insert x plus h in place of x into this expression. So we're going to go through and do that. Okay, so I'll just highlight here to remind us what the function is. So this is x squared minus 2. And so let's write down this definition here. So g prime of x is the limit as h goes to 0. Okay, so the first thing we have to do is insert x plus h in place of x. So this will be x plus h squared, and then minus 2. And then we have to subtract off the function itself. So we have to take away x squared minus 2, and then divide by h. So this is the most important part of setting this up, right? If you look at this, you can see g of x plus h, right? It shows up right here. And then you have to subtract the function itself, and then divide by h. So once you set this up, it's a lot of algebra that you have to do, and then at the very end, take the limit as h approaches 0. So I'm going to do some of that algebra right now. So the limit as h approaches 0. So there's nothing interesting here on the bottom. So you can multiply all of this out. So this will be x squared plus 2hx plus h squared. Right, so you get the trinomial out of that, and then minus 2. And then you can distribute the negative. So negative minus x squared, and then plus 2. So if you look at what we have now, notice we have x squared and negative x squared. So those will add to nothing. and then also minus 2 and plus 2. So we get this development here. And then you can look ahead and see that there's a common factor of h, right, upstairs and then also in the denominator. So I'm going to factor that right out. So that's going to leave 2x plus h. Okay? And remember, we're letting h go to 0, so it's valid to cancel these out because h will never equal 0. And then we're left with 2x plus h. Okay, so in the end, now h can travel to 0. And so this part here will go to 0, and you can see that the 2x is going to fall right out. So this is equal to 2x. So the connection to make is that this 2x, right, is equal to g prime. So go way back here. So that is going to give us the derivative of g at x, or the slope of the tangent line. Okay, so we can get rid of this work, but this is what we need to finish off the problem. Okay, so we'll transfer that right there. And so the original problem said find the slope of the tangent line at 3 different locations. And so I believe it was x equals -1, 0, and then also 2, right? So this is a dynamic function here where this derivative depends on the location, right? It depends on x. So we can just plug these numbers right in. So if you insert -1 in place of x, the first one we can show some work, right? So the first one you get is -2, and then g prime of 0 is going to equal 2 times 0, so that's just 0. And then lastly, g prime at 2, this is going to be double 2, or 4. So the big thing is, this is just a calculation, but these numbers here indicate the slope of the tangent line at these different locations. Okay, so every single one of these numbers. And so it's really telling you that your function is twisting and turning, right? It's bending in some way. So what I'd like to do here is just to take a look at this graphically. So the original problem, right, was the parabola g of x is equal to x squared minus 2. So if you want to think about this, what you would want to do is to graph this function and then to draw the tangent lines at these 3 different locations, and then you should be able to see that the slope is changing. So I have a graphic here of y equals x squared minus 2. It's a pretty fundamental one here. So I'll put it up right here. Okay, so you can see the parabola x squared minus 2. The plain old graph here just dropped down a couple of units. So the big thing is trying to interpret what this means. So this first statement, right, g prime at -1 is equal to -2. That means if you find x equals -1, the slope of the tangent line is going to be -2. So if you look over where x is equal to -1, and then you drop down to find that spot right on the curve, this -2 here is indicated by the slope of the tangent line. So you can draw a little line right in here, just like that. And that's what this number means, right? So the slope here, m, is equal to -2. Okay, so this one here, also very believable. So when x is equal to 0, the slope of the tangent line is 0. So notice when x is 0, we're down here at -2, and the tangent line looks perfectly horizontal. So you can see right there, m is equal to 0. Okay, and lastly, when x is equal to 2, the slope of the tangent is now 4. So we find 2 here and go up to the curve. So that's right about here or so. And you can see the steepness of this tangent line here. So it's right about here or so. Like that. Okay. So now you can see that the slope is changing. So the slope here, m is equal to 4. So you can tell, depending where you are on the parabola, the tangent line changes its steepness, right? And then you can calculate that, and that's all based on this g prime of x, right, equaling 2x.